Thank you, Dave, for sending some note where there are. I try to collect some exercise which during the lectures I would say this may be interesting to do if it's the first time you have seen it. It's some very basic linear algebra. If you want to discuss this tomorrow, I'm very happy to do that since there is a problem session. But if you have some more interesting and challenging problems, we can discuss that all together. That will make the problem session even more interesting. So everything I said yesterday was some very basic known theory about universal enveloping algebra, Yangians, and invariant theory, but I forgot to give credit in one case. So this way of constructing central elements of the universal enveloping algebra, which was achieved by computing this row determinant of this kind of Casimir plus shift matrix. So this is known as Capelli identity, or maybe this is known as Capelli determinant, which follows by Capelli identity. But let me say this is known as Capelli identity. So I forgot to mention this yesterday. And how did we construct the analog of this polynomial, which now doesn't contain all the generators as a polynomial algebra of the center, but of the W-algebra? We apply this map construct by Kashdan and constant. And the main feature is that even though this is just a linear map, it behaves very well for the row determinant, so we can bring inside. So this is more or less the last part. And the idea is, or maybe the motivation is, let's try to generalize Capelli identity to any W algebra. And when I say W algebra, I'm talking about finite, quantum finite. And I briefly said, if we want to do it in general, we should replace this row determinant. And the reason is some counting dimension reason. I mean, it was explained today by Thibault that the Zlotov slice has the same dimension as the centralizer, the dimension of the centralizer of F. So if we now do this for GLN, the centralizer of this principal nilpotent, for which this case consists, is just n, like the rank of the Lie algebra. So if we now write down this row determinant, if we pick the coefficients of each powers of z, we get the generators. But if f is different, the dimension increases. So if our goal is to achieve all the generators, we need something which is bigger than this polynomial. That's the main reason why this doesn't work. And one observation is that up to the sign minus 1 to the n, this row determinant is the same as what is known as a quasi-determinant. So let me explain what is this quasi-determinant. So this is a good candidate because it coincides at least for principal nilpotent. So the quasi-determinant is as follows. And this was defined by Gelfand and Retak. So we just pick our matrix A. We write in block form. So let's say alpha, oh, let me say for some reason B, A, C, and D, or maybe I should D and C. And what kind of block matrix we want? A is a 1 times 1 block. So B is some horizontal vector. C is a vertical vector, and D is a square matrix. So this quasi-determinant is defined as A minus B D inverse C if D is invertible. So you may check that it coincides in this particular example with this row determinant. But let me try to give a little bit more general definition that will be more useful for us. But the philosophy is just the same as the definition by Gelfand and Retak. So in order to do this, I need to introduce a little piece of notation.
So I wanted to know, is there a definition for this quasi-determinant if D is non-invertible or?
No.
Okay, cool.
Also, yeah. It needed to be invertible, yeah. So let me just write this notation. So let's say it's a lazy notation. So if B is the direct sum of two vector space, let's say U and U tilde, So let's denote with this symbol. So the identity of U will denote three objects. So that's why it's called the lazy notation. So either it's just the inclusion map, or it's just the identity map, or will be just the projection map with respect to this decomposition. So the kernel will be U tilde. So if you think a little bit, they're all the same map. Okay, now let me try to define this quasi-determinant using these maps. So assume that our vector space comes with two splittings. Yeah, and I didn't say. So if I don't make mistakes in the lecture, the notation will be always clear from the context. So let's see if at least I can achieve that. So we take a vector space with two splittings. And then here we are taking a matrix. And remember that our matrices have non-commutative entries. So assume that our matrix A, and we are working on, say, R is the universal enveloping algebra, so it's a unital associative algebra. So we assume it's invertible. And also the following element. Oh, this always makes me confused. So you see, I already made, no, it's correct. Also, the following element is invertible. So, okay, let's see how to understand this notation. So what kind of map is this? Well, at a certain point, we have A inverse, which is a map from B to B. And before applying A inverse, we are applying this identity map. Let's have a look. There is just one map whose target vector space is B. So this can only be the inclusion map. And now at the end, we need to apply the identity of W. So there is just one map which starts at V, which now is, sorry, yeah, which starts at V and ends at W now in our case. So this is an element in R tensor from U to W. So, and the inverse will be an element in R tensor from W to U. So if this happens, then let's give the definition of a quasi-determinant, a little bit different than what is given here, but equivalent. So in this setup, we define the quasi-determinant of A in position U. And so its inverse will be the quasi-determinant. So this is an homomorphism from W to U. Okay, let's see that we get exactly the same definition, but this will be more useful for us. So now let us write A in block form as follows. So we write A, B, C, and D. How do we write in block form? So we have two splittings. So usually when we write an endomorphism, we choose the starting base to be the same as the final base. So now let's choose the starting base in W and W tilde, so according to this splitting, and the final base according to the splitting U plus U tilde. So here we have W tilde, and here we have U tilde. So if you want, according to the notation, so small a is just what? We embed W into V, and then we project into U. And so on, okay? So now this is a simple linear algebra exercise. So say that the dimension of U is equal to the dimension of W, and that A is invertible. Then we come at the question that you say. So if the quasi-determinant exists, then D is invertible. And if this is the case, then this quasi-determinant is equal to A minus B D inverse C. So it's necessary that D is invertible. And okay, let's do a specific example just to give some ideas. So let's say V is an n-dimensional vector space, and let's fix a basis. This is. So we just denote U to be the one-dimensional vector space generated by V1, and U tilde generated by the remaining basis elements. So W is the one-dimensional vector space generated by Vn, and W tilde by the remaining ones. And let's write A in this basis V1 up to Bn. So it will appear as follows. Okay. So now I think there is no reason to reorder the basis because are smart enough to write this without reordering. So let's put the basis of W tilde in front of the basis of W. Then let's denote this by A. Let's denote this by D. And let's call this A and B. Then according to the proposition, this quasi-determinant in position 1n is exactly A minus B, the inverse C. So as we should expect from the original definition of Gerf van der Retak. Okay, the idea is to construct an operator using this quasi-determinant, which contains possibly all the generators of the W algebra. And the reason why we are taking this quasi-determinant is because in some sense, we generalize to this setting, or it applies better to this setting than the row determinant. So let's review a little bit about the definition of W algebra. Are there any questions? Okay, yeah, sorry for this linear algebra interlude. Okay, let's remind a few things about this definition of W algebra. So we have a reductive, finite dimensional reductive Lie algebra. So this means in particular that we can find a symmetric invariant non-degenerate bilinear form that we are going to fix later. Then we choose an nilpotent element or a nilpotent orbit, but let me always think about element. So in particular, then we can find a copy of SL2 inside our Lie algebra G. And we have a decomposition of G with respect to the joint action of H. On each space, the joint action of H acts as multiplication by 2k. And it follows from the fact that this is finite dimensional that there is a largest eigenvalue. Let's call it D. So let's denote this by D, the largest eigenvalue. And then attached to this, we have two nilpotent subalgebra, just G greater than 0, which contains G greater or equal than 1, nilpotent subalgebra. Okay, using this, we construct a linear space, and then we consider the invariants. So let's denote this linear space by, it's a left mode. So let's denote this by M. It's this quotient of the universal enveloping algebra by this left side ideal. And the W algebra was defined as the invariant with respect to the joint action of the bigger nilpotent subalgebra. So let me just write W since it will be fixed from now on. So this was something we already mentioned yesterday, was already reminded this morning. So now we need to construct a certain operator. So this operator should act on some object, on some vector space. So let's fix our vector space. So and this vector space will be just a finite dimensional representation of G. And so it's not important, but let's say it's faithful. Eventually, if we don't ask it's faithful, we may get a lot of elements in the W algebra, but this will be all zeros. So it's not very nice. So let's say it's faithful. And let me use the following convention. So if we have some element in our Lie algebra, we will denote with lowercase letter. But if the same element is considered as an endomorphism, so let me use uppercase letter. And moreover, since we have this representation, our Lie algebra is reductive, let us fix the bilinear form. And we just want to be the trace form of this representation. Okay, so we need some data to define this operator, but I hope it will be not too boring. So now we have an SL2 triple. H is semi-simple inside G, and it acts semi-simple in any representation. So we can consider the decomposition eigenspace, let's say, the H eigenspace decomposition. So let me denote as follows. So again, here H acts as 2k, and the largest possible eigenvalue is now D over 2. And we can consider also the same decomposition for the space of endomorphism.
Why is it divided by 2 now?
Yeah, maybe I will give an example. Let's see if we
Okay.
manage to understand.
Thank you.
Yeah. So we can consider the at big H the composition of NV. This is more or less the same as the composition of G, but there may be more elements in the endomorphism of V. So let me do the same. So add H at that's multiplication by 2K. Yeah, what I need to say. So this is more or less the same decomposition at G. So the largest eigenvalue is also the same. It's this number that we have denoted by D. So it's not so important for us, but I wanted to give an example later. And before giving this example, so I would like to use this notation to give an example of a shift matrix, which will be introduced later. But before giving an example of this decomposition, let me just remind some facts from representation theory of SL2. So what happens to our vector space V? So it's the direct sum of V plus and F applied to V plus. Now let me explain later what is V plus. And V minus direct sum E applied to V minus. So what is V plus? So V plus, if you want, is the kernel of E. These are highest weight vectors. In the notation which I have discussed, it's just the space which has highest eigenvalue. The eigenspace with us highest eigenvalue. So we start with an highest weight vector, we keep applying F, and eventually we get all our representation V. And similarly, this V minus consists of lowest weight vector, and it's just the space, eigenspace of lowest eigenvalue. And of course, FV plus and EV minus will be just the obtained from that direct sum decomposition in some easy way. Just everything which has not degree eigenvalue d over 2, and everything which has not eigenvalue minus d over 2. So this motivates why we wanted to define the quasi-determinant using these two splitting. This formula for the quasi-determinant that we want to compute will be in position v plus v minus. So, but let me give an example of all of this, and then probably I hope these numbers will be clear. So let's do a very basic example, SL2. Take our H over 2 eigenvalue. So F as eigenvalues minus 1, H has commute with itself as eigenvalue 0, and E as eigenvalues 1. So now let me write the decomposition for this vector space. Let's say V is the two-dimensional representation. So we have F. So this is a four-dimensional vector space, and the add H over 2 eigenvalue. This is now the same for all the elements of the, and the identity has degree 0. So now we need to split our representation. Okay, so let's write explicitly what is H. So on each space, H acts as 2K, right? So the eigenvalue will be divided by 2. So V1, if we take V1 to be this vector, H times V1 is 1, but we are taking half of its eigenvalue. So with respect to the H over 2 eigenvalue, this will be 1/2, and this will be minus 1/2. Does it answer the question? Okay. It was very basic. Yeah.
And this can be proved for an abstract faithful representation. You can.
Yeah.
Okay.
Yeah. We are just using properties of SL2. Yeah. This now is SL2 itself, but also for any other algebra.
So I think maybe the confusion was that you used D before for the adjoint representation, and now when you change to an arbitrary representation, you were using D over 2. But these aren't the same, right? They're totally different.
Yeah. The fact is that, when we use the eigenvalue for the joint representation, what do? We sum this element on the diagonal with this element at the diagonal. And so this is, we'll have 2. If you have a bigger matrix, we need to do this process several times. When we apply to this, we just need to take this. So the sum is divided by 2. And I always got confused with this half integer eigenvalue. We can get rid of this. But once I asked Professor Katz, why do you keep want to use this half integer eigenvalues? And he replied, because the spin of electron is 1/2. So, I still don't understand. Yes. Okay, sorry for all this notation, but now we can introduce the object that we need, or maybe not really now. We still need to fix a basis to define our Casimir. The Casimirism does not depend on the basis, but let's fix it. So let's fix a basis UI of G, and U upper I will be the dual with respect to the trace form, which I raised. And also, let's take this basis to be compatible with the decomposition of G. So we want this to be homogeneous. And I will denote this eigenvalue with delta I, just to save a little bit of space. Okay, once we have all of this, we can finally define the two main objects, which appear in this argument of the row determinant. So symmetries and another shift matrix. So the first, I think I denote by E last time. Sorry about this. So this is just the Casimir of the representation. And I know it created a little bit of confusion last time, but let me assume that elements in the universal enveloping algebra are coefficients. So let's get rid of this tensor product on the first term, which was the problem for this matrix omega last time. So it was something like omega times the one in the universal enveloping algebra. And let's define this shift matrix as follows. So we take the sum over all basis element of G greater or equal than 1 of this operator. So now this is an honest matrix. And moreover, we are multiplying dual elements. So it's an element of degree 0. So it has some nice properties. So not only it has degree 0.
So sorry, is this, I wasn't listening before. Is this just the quadratic Casimir in?
Yeah, it's the Casimir of the representation. Yeah.
Yeah. Okay. Cool.
The same matrix as we wrote yesterday for GLN, which was denoted by E.
Thanks.
So let me state just this property of D. So it has degree 0. So you may think it's diagonal matrix, but not really. So it commutes with any other element of degree 0. And moreover, if an element has degree 0 in the Lie algebra, it commutes with H. So in particular, all elements in the Cartan subalgebra belong to G0. So this matrix commute with all elements of the Cartan subalgebra, Cartan subalgebra. So meaning that it's very nice operator. It preserves the weight space decomposition of G. But it does need to act as a scalar on each weight space. So it's you may think it's a little bit alpha Casimir, but it's not like that. Anyway, it has nice properties. And let me just write what is D in this case.
Is the discrepancy to being a Casimir just missing out the less than 1?
Yeah, exactly. Yeah. Let's write what is D. So what is a basis of G greater or equal than 1 in this case? It's just given by E. The dual will be F. So this matrix is just minus E times F. So this is the same matrix which we have used yesterday when writing down Capelli identity in the specific example of SL2. But it has a very nice combinatorial property. So we can just write this. Another example, if we take GLN or SLN, just let's take the standard representation. Then this DS is the following operator.
So Daniel, can I clarify something here?
Yeah.
Are you fixing a choice of nilpotent so that we have a particular?
Oh, yeah. It was fixed at the very beginning.
What did we fix it as?
F just nilpotent.
Which one though?
Any nilpotent.
Okay, but surely the what lies in G greater than or equal to 1 depends on which nilpotent we choose, right?
Yeah, exactly.
For example, this calculation here doesn't work if I take the 0 nilpotent, right?
Yeah, because in that case there is no SL2 triple etops. Yeah, so let's say any non-trivial nilpotent. F equals 0, we should think like we do not perform Hamiltonian reduction.
Yeah, okay.
But yeah, we fix any nilpotent and then we can apply all this machinery. And one good choice to be just take it in already in normal form. Jordan form, sorry.
Okay.
Okay, one can prove this. And this is something very nice. If we now take the trace, we get this identity, which So I never seen this identity. It should be some simple combinatorial identity, but it just follows by writing explicit this matrix D. But I don't know the meaning of it. And this, if you're interested, this could be a nice exercise to check that this shift matrix D has the following form. And by taking the trace on both sides, we get this. Sorry, there is B. Yeah, it relates the dimension of G to the dimension of the representation.
This also only type A.
No, any type. The formula for D? Yeah, only type A. There is a similar formula in type B, C, and D. Yeah, the formula which I wrote before with the. Oh, this doesn't hold in type B, C, and D. We need to modify a little bit. We need to add some extra term. But the previous formula holds in general. So I think, okay, I think it's done with the definitions. So now let's see if we can construct this Lax operator. Okay, so the idea is to start with this Lax operator for the universal enveloping algebra. So let's say some kind of ancestor Lax operator. So just a polynomial with entries in the universal enveloping algebra. And it acts on our representation V. And then if you remember what we have done with the Capelli identity, we apply rho to this matrix A. But now there are a little bit of problem. Let me just define this element. So let me call it A upper rho. So this is still an element in the universal with polynomial with coefficient in the universal enveloping algebra, and it acts on our representation. So what is U less or equal than 1/2? We just take our UI to run over a basis of G less or equal than 1/2. So we just take a little bit of U. And let me try to explain a little bit why. So roughly speaking, A rho is more or less rho of applied to A of Z, as we have done for in the Kashdan constant theorem. But this is false. I mean, this is clearly false. And why is it? Because Kashdan constant map takes values in our module M. Our element takes value in the universal enveloping algebra. But it's not far from being true. So how we should understand the A rho of Z? So let 1/line denote the image of 1 in the universal enveloping algebra in this left module M. Okay. So if you want 1/line, it's just 1 plus this ideal. So it's an element in the quotient space, it is just a left module. Then if you apply A to 1, then this is the same as applying A rho. So the main difficulty is that M is not an associative algebra. So we cannot apply rho so easily. And we would like to compute some quasi-determinant. We would like to multiply object. So the idea is, okay, let's try to stay in the universal enveloping algebra where we can multiply objects.
Sorry, I just don't understand something. AZ is supposed to be at the same time applying some operator on UG by left multiplication and something in NV. So one is a tensor by the identity of V or something like that? Or?
Yeah, yeah. Thank you. I keep doing this. So let's say in this line should be really.
Okay, thank you.
Thanks. I keep forgetting. I mean, when there is no sign, it means we are tensoring with the identity. So let me maybe state now the theorem and then try to give some ideas. The result that we prove with the Sole and Katz is the following. So we let L of Z to be the following quasi-determinant. Oh, that's was okay. It was denoted by A rho, but I rewrote it. So we compute the quasi-determinant of this A rho, which is the analog of rho of A in the Capelli identity. We shift by our shift matrix, and the position that we want to compute is this position B minus B plus, consisting of lowest weight vector and highest weight vector. So then we get a Laurent series with coefficient in W, and it's an homomorphism. Sorry, here should have B plus B minus. It's an homomorphism from lowest weight vector to highest weight vectors. So there are several statements in this theorem. So let me try to maybe give an idea. So maybe there are just two statements, not several. Let me state like this. There are two statements. And of course, this we need to apply to one. So it contains two statements. So the first statement is that this quasi-determinant exists, because as we have observed, we need to invert some metrics. And the second statement, so let's say that this statement is this equality, namely that this exists. The second statement is that the coefficient lies in the W algebra. Are there some questions, further questions? Yes.
So each coefficient gives all generators? Or?
Yeah, no, not really, because this is a Laurent series, so there are infinitely many coefficients. We need to pick some of them. We can write in a specific form. Let's say we can write as a rational function. We pick up the coefficient of these rational functions, and they will form a system of generators in the PBW sense.
Oh, okay.
Maybe I will explain this in the explicit examples.
And also I have one more question.
Yeah.
You say LZ is a Lax operator, but why it is called Lax
yeah.
operator?
Yeah, thank you. Because it was first introduced for classical affine W algebras. So similar similar definition, much easier because everything is commutative. And using this operator, one can write hierarchies of partial differential equations, which can be written in Lax form. So in that setting, we call this Lax operator, and we kept this terminology.
This is for any G.
Yeah, any G, any F, any representation, faithful representation. Yeah. And I will try to give some ideas on the computation which are involved in the proof. So basically, for the existence, it is kind of very nice, just a geometric series. So you can give as an exercise to your calculus student.
So Daniela, there's a question in the chat. Vidas is asking if the left-hand side of your definition, the quasi-determinant, is actually a polynomial in Z.
Oh,
On the
no,
right-hand
it's
side of Z inverse. This is because the quasi-determinant involves an inverse, right?
exactly, yeah, because we need to invert some metrics. Yeah, by explaining a little bit, I mean, I don't need to explain to you what the geometric series is. How to use the geometric series, we will see that there will appear some inverse powers of Z. And this is a little bit, this is also easy. This is just easy computation using the properties of quasi-determinant. Okay, what is not very easy is, let's say, 1/2. So 1 + 1/2 is not a statement, but it's the hard part. It's just some hard part involving the use of some objects which are known as Riesz algebras. So let's see if I can give some ideas of all this. But if it becomes too dense, please let me.
Sorry, I was wondering why there are infinitely negative terms in the Laurent series. Is it because we have a double inverse in the formula?
Yeah, let's see. Let's see a little bit of how to achieve part one, and let's see how many coefficients we will get. Is there a little bit of more chalk? Thank you. Thanks so much. Thank you. See a little bit. So, for example, okay, let's try to do this simple linear algebra exercise. So here there is was a determinant. Before applying it to this element one, let's try to compute it. Let us assume that this definition, I already stated it, I think at the beginning. So in order to exist, we need that A rho of Z plus D invertible. And then we need in some space, let's write it later. So these are our two requests. And so let's start with the first one. I have enough space. So let's write down explicitly what is A rho Z plus D. So it's the following element. And then now we use geometric series. So we just write this as Z. And now we try to invert. And here we can use geometric series. And I think this is the only way we can invert it because it's a polynomial. So the only polynomials that we know how to invert are the non-constant, constant, for which the constants are invertible. We are working over C, so just non-zero constant. So the only way we can invert is as a Laurent series. So this is why our final result will be a Laurent series. And now let's see what happens to the second part. Okay, now let's just copy everything, but on the left, we need to add this identity on B minus. And on the right, this identity on B plus. Okay. Oh, sorry, I forgot plus B. Everywhere. And we have this object now. And let's remind ourselves that these are highest weight vector, and these are lowest weight vectors. And in the middle, we would write a map which moves us from highest weight vector to lowest weight vector. So D has degree 0. We already noticed it. So if we apply D to highest weight vector, we are in the same space. So we still get an highest weight vector. So in some sense, it doesn't move this B plus. So we are stuck on B plus. U less or equal than 1/2, this has degree, the endomorphism part, greater or equal than minus 1/2. So if it is 0 or bigger than 0, so if it's bigger than 0, then it kills any highest weight vector. If we apply the 0 part, we are stuck in this highest weight vector. So the only option that we can, if you think about representation theory of SL2 as some strings, we can make a step on the left by minus 1/2. And we want to make these steps until we move from highest weight vector to lowest weight vector. Okay, so this is the most possible situation. But now let's look at F. F is much faster because it makes a step by minus 1. So whenever we apply F to a highest weight vector, we get another vector, which has degree smaller than 1, not smaller than 1/2. And how many steps do we need to do to go from highest weight vectors, lowest weight vector, applying F, exactly D times, which was the degree of our decomposition. So what I want to say is that if L is less than D, we get 0. If L is D, we get this isomorphism. So eventually this object here, lower order terms, this is invertible because it's an isomorphism. And we apply again geometric series to get the inverse.
Danielle, is this some notational thing, but should that F have a power?
Oh, yeah, thank you. F to the D.
Good.
Yeah, sorry, it's this isomorphism, which identify any highest weight vector, which are lowest weight vector. Yeah, thank you. So basically, this first part is just using geometric series. And so where does this belong? The highest power is negative, so we never create infinitely many high powers of Z. So powers of Z will always be bounded. Okay, this was just to give some ideas, but basically just using geometric series, and this is why there are these Laurent series appearing here. And now let me just write a little bit why this is easy and why there is this hard part in the middle. Okay, so we have shown that this quasi-determinant exists. So, but the hard part is to show the following, that it's also equal to another quasi-determinant, which I don't want to talk about, but just I'll try to give an idea in an example. So this is the so-called Riesz module associated to M, and it is contained in this space of Laurent series. I'm just talking about this, okay? So let's avoid to write homomorphism part. And this, which I'm not going to define yet, this object belongs to the Riesz algebra of U of G. And actually, when we compute quasi-determinant, we need to invert something. Do you have a question?
Just maybe I can let you finish.
We need to invert something, so we need to localize this Riesz algebra. And this is also contained in some completion, let's say. Anyway, it doesn't matter. Let's say it's contained in this. And the Z minus D applied to UI is just multiplied by these powers of Z. And remember that delta I is an integer eigenvalue, so that's why this Riesz algebra is defined with this square root of Z. So if we can prove this, then the proof of invariance is very easy. Let me just try to give an idea.
Is your quasi-determinant supposed to be applied to 1 bar or something like that?
Oh, yeah, thank you.
Okay, thank you.
And basically it follows from the property of quasi-determinant and of the Casimir, the invariance. So we would like to show that this is 0 for every positive, for any element in this nilpotent subalgebra. And so this is equivalent. This is defined as the inverse of some element. So if A commute with the inverse, it commute with the element itself. So this is the same as asking that. Okay, now let me call this for simplicity B. So let's try to compute this. Okay, what do we get? We get, so recall that in this formula holds in any Lie algebra, in any universal enveloping algebra. So let us apply this. So we get the identity of B plus, B inverse, A, B, Z, B inverse, the identity of mu minus. And now there is a nice properties of Casimir elements, which is a nice exercise to do. So if we take the commutator of A, which is something that contains the Casimir element, it transforms small a in big A up to change its sign. But since we are applying this operator Z to the minus delta in front of A, we need to keep track of the degree of the eigenvalue of A. But you can set Z equal 1 if you want. So now we get two terms. So let's multiply by Z in front of everything. So what do we get from the first commutator? B of Z capital A. Okay, now so this cancel. This cancel. And let's have a look at what we have. So we have, I made some mistake. Yeah, this was B minus, sorry about this. So this should be B minus B plus. Seems like it was going to be, sorry about this. Anyway, what happens? We are starting from an highest weight vector. We are applying some positive operator. So this is 0. And then what happens in, sorry, this I'm making a lot of confusion. Okay, so A, B plus was here. Sorry about this. So we start from a highest weight vector. We act with the positive part of our Lie algebra, then we get 0. So this term doesn't contribute. On the other end, here, no matter where we start, we are moving on the right, let's say with our positive operator, so we can never reach a lowest weight vector. So this is again 0. Okay, just in this proof, we only use these properties of the Casimir element and this definition of quasi-determinant, and it allows to construct a lot of invariants. And let me just give one word about this R part. And the main thing is that in the R part, it doesn't appear to be the shift matrix. We have a question about this. Sorry about I got confused with these two lines. I should have written an extra line without B and B inverse.
I think I probably missed this part over here. You've got the commutator of A with B of Z, and you've written it as the commutator of B of Z with A.
Yeah, this.
Why is the bracket not anti-symmetric?
That's the sum of A U I U upper I. And then we can use the bilinear form. And by invariance, so this is the same as UJA. And now we can sum again over I. And when we sum again over I, A is put on the left. Because it's invariant, but it's, let's say it's minus, it's invariant with respect to the dual, let's say. So we need to keep track of this minus sign. Yeah, I will add to the exercise. But it's just a basic property of the Casimir. And the fact that these two maps cancel is a basic property of the quasi-determinant. So if we think that usually computing invariance or computing homology is quite difficult, I mean, it's rather involved. But apart from this mysterious part, the computation which show invariance are very easy. So let me just try to give an example on how this Riesz algebra work. Let's keep SL2. So now we need to multiply our Casimir element. Okay, let's write the Casimir element first. So maybe let me denote by x h over 2. So the Casimir is just x f e minus x. So we need to multiply by these, let's say, minus delta eigenvalues. So let's write the minus delta eigenvalues. So this is minus 2. It's minus 1, minus 1. Minus 1, 0, minus 1. 1, minus 1. And I think I made another mistake. I just realized from this that I need to multiply by some power of z in order to make it. But it's not so important. Eventually, the multiplication with this power does not impact the invariance. And then, okay, we need to also add the identity. And now let's compute this quasi-determinant in position v minus, v plus, v minus. So this is v minus, this is v plus. So, sorry, v minus and v plus corresponds to the representation. So this quasi-determinant v minus v plus is the same as we put in position 1, 2. You always keep inverting that, sorry. So this is the usual quasi-determinant in position 1, 2. So we are taking this position, so we get z minus 2, f minus. So we should think that in the real algebra, which is a localization, E inverse exists. So this element exists in the Lie algebra, in the RIS algebra. So we are localizing in such a way that we can compute this quasi-determinant. But then if it exists, so we know that x E minus EX is 1. And so this is telling us that, of course, this is constructed in such a way that the relation of the universal enveloping algebra extend, then EX is just equal to x plus 1 E inverse if we commute. So the same relation of the universal enveloping algebra has to be satisfied. And let me write something like 1 inverse. And now we need to apply everything to 1, as Thibault just reminded us. And again, so what's the, here I have E inverse. So what's the property of E applied to 1? E lies in the positive part. We need to replace E by the trace of E and F. This is just 1. And then if this relation is satisfied in the RIS module, because we want that it extend our module M, so E inverse 1 is 1. And then we get the following object. I think I put Z minus 2 here. Sorry. So this becomes Z. And so this is the same as this quasi-determinant, which is what we have denoted by A row of Z plus the shift which you computed before. So it seems mysterious that this identity hold, but the fact that we apply this quasi-determinant to 1 makes appearance of this shift matrix, which was also hard to compute explicitly, but we get an explicit formula. Yeah, sorry for so many mistakes. I hope that the examples a little bit explains what's going on. Thank you.
We have time for a couple of questions. Maybe I can make a naive question. So this RIS algebra and RIS module that you talk about, is it in any way related to localizations? I mean, normally you couldn't localize because E actually acts nilpotently, but is there some relationship?
Yeah. So the idea is the following. So there is a cache down filtration on UG.
Yep.
And we extend this filtration by saying that Z has degree 1. So there is algebra is very easy to define. Just take the 0 component with respect to this filtration. Okay, now the ideal, which we are going to quotient by, it's not written anywhere. So this UG times this shift by this character, it's kind of a maximal ideal. So when we quotient, we get a field. And then we get some kind of evaluation map of the elements in this, of any element in principle, okay? And when this evaluation map is non-zero, it means that we can invert. Like, for example, if you evaluate E, we get 1. So we can invert. We add all the possible invertible elements to our algebra, and we get something that we call by R1 of UG. The problem is that maybe it's not sufficient to compute quasi-determinant. And so there is a standard procedure. So we keep applying our evaluation to all the elements R1 of UG, and we invert everything. And we invert everything. We invert everything until we get this direct limit. So this is how this localized real algebra is constructed, more or less. There is a lot of computation to show that it acts on this module again, because of course it's not guaranteed that this direct limit acts on the module. And yeah, it's some technical, but I hope at least it explains why these shift metrics appear, which once you know that something should work, it's just a matter to plug, let's say, okay, I know that this identity should work, let's plug it and try to guess what is D. And if you're lucky, you can guess what is D. And
Vidas asks in chat whether all of these computations are shown in any of your papers, and if so, can you give us a reference?
Oh, yeah. And I hope to give some examples which are quite easier than the theory. So there are these two papers in the Sol and Katz and finite W. There are explicit computation for GLN, and there is another paper where we deal with the general case, and they're both on arXiv. There is a link on the web page of the event.
Okay, thank you very much. Another question?
Is there an equivalent? Thank you. Is there an equivalent development for Poisson algebras instead of associative algebras to compute the generators?
No, but it should be. One should take the classical limit of all this procedure, and in that case, it should be easier as in the Poisson vertex algebra case, since we are not working with any module, so we are just quotienting by a Poisson idea, commutative algebra idea. So there is no problem. Multiplication is well defined, so it should be a little bit easier.
Okay.
There is no need to go through this RIS algebra, and there will be no shift for this reason. So everything is classical. So the grade, associated grade is obtained by sending D to 0 in some sense.
Thank you.
Wonderful. Any last questions? All right. If not, let's thank Daniele once again.